This is a series for self-learning computer science. This is not a formal course. This is just an arrangement of resources and topics I wish I had knew earlier. So first, I assume you are a technical person. By technical, you don't have to be a geek who already knows how to program or how electronics work. You are in general curious about the modern world and modern physics. I assume you have a basic knowledge of physics and electronic circuitry, and I assume you have heard the terms semiconductors, transistors, logic gates, and truth tables, although you don't necessarily need to understand how they work. Just a gist. In fact, anything you learn today probably will never be used in your daily life. You will probably forget half of it anyways, so don't stress out if you don't understand anything. The point is to get the gist across, not the technical details. So let's talk about semiconductors. In fact, I'll let one of my favorite guy on YouTube, Ben, talk about it. Go watch his 15 minutes video on this topic. Done? Nice, now you know how a semiconductor works at a fundamental level, or at least have some idea of it. So what now? Well, when you have some semiconductors and you can arrange them in a certain way to make something called a transistor. Transistors are way more interesting than semiconductors because they have some special behaviors. You can watch this video from the same Ben. You can see he's my favorite about transistors. Got the idea? So the main concept of a transistor is it's basically an automatic switch. So when you connect a circuit, it should run on electrical power, right? But you still have to manually turn on the switch to start the circuit, like the switch of your fan or light on your outlet, right? But with a transistor, by applying the right amount of voltage to the base, we can turn on or off a switch with electricity. So we basically run a circuit through the circuit itself. Cool, right? But why? Well, similar to semiconductors, when you connect the transistors in a certain way, you get even more interesting behaviors. You want to know how? Watch this video from who. Right, logic gates. So this is where the fun begins. This should start to get a little bit interesting now. So one thing before I actually conclude to the final revelation, we still haven't mentioned how logic gates can actually do maths. It's actually less complicated than you think it is, so you have to check this playlist by another genius on YouTube, Sebastian Leak. Go watch this video and then you'll understand what I'm talking about. Right. So, perhaps you've heard of Alan Turing. If you haven't, look him up and watch the movie The Imitation Game while you're there. So, Turing gave a theory called Turing completeness. It is one of the fundamental theories of computer science. Along with something called the De Morgan's law, if you can have some physical device simulate these logic gates, like we are doing with transistors, and assuming you have an infinite amount of them, you can call a system Turing complete. And if a system is Turing complete, it should theoretically be able to calculate most mathematical things, which we call a calculator or a computer, because a computer is just an overgrown calculator. The general idea is that the logic gates are what separates your computer or a phone from a hammer or a screwdriver. You don't even need transistors for logic gates, to be honest, because you can make the same computer using more clever ideas. People have made binary adders and gates using marbles, water flow, and many more. It just happens that transistors are fast, small, and can be manufactured at an industrial scale. So we happen to use these for computers. So, do you need any of this to know how to program a computer or just learn programming in general? No. Most computer engineers never need this beyond passing their undergraduate degree maybe. However, it is compulsory for anyone who wants to work with computers to have an idea of what is going on under the hood of their Python program or web app that they're making. Because at the end of the day, it all just boils down to neat computational theory, logic gates, and electrons. So even if you don't understand everything in detail, at least try to have a general idea of what a computer might be doing or when you are trying to do anything on it. Even if you're wrong or not 100% accurate, it's a good habit to always try to figure out the bare metal workings of any system while working on the abstraction layer of it. Thank you.